All right, what's going on, everybody? We are here in the second video of week 13. We are in the middle of chapter 11 now, our conclusionary chapter of the semester. And today we're going to look at the integral test and estimating sums with integrals. The first two sections of this chapter, we looked at first sequences, then series. But ultimately, what we saw is that I should change this to just say series, is that it's difficult to judge whether or not a series is going to converge or diverge. And then, even if you know that it converges, determining what it converges to is also not necessarily a very easy thing to do. What we're going to see today is that if we can visualize a sum, a series, geometrically, then we'll see that it's going to be pretty easy for us to compare that area in a graph to an area associated with an integral. And then we're going to be able to make integral comparisons, saying this integral compares to this sum in this way, and I can see it visually. And that will help us determine if the sums should converge or diverge based on whether the associated integral will converge or diverge. Then, even further, if the sum converges, then we can use integrals to estimate the value of that sum, right? So what we want to look at is how can we use integrals to help us determine whether a sum is going to converge or diverge, a series is going to converge or diverge. And what we're going to do for our first example today is we would like to determine if the sum or the series 1 over n to the 1.2 will converge or diverge. What we know so far is that the harmonic series, the sum of 1 over n, that thing definitely diverges. We looked at two different proofs of that in the last video. I can tell that the values 1 over n to the 1.2, all those values are going to be like a little bit smaller, right? Because we're dividing by a slightly larger number because we're taking a slightly higher power on n. So what I'm thinking is that that sum should certainly be smaller, but the question is it smaller enough to make it converge, right? I could take something that diverges off to infinity and subtract 1,000 from it. It's technically smaller, but it's still diverging to infinity. 1,000 minus infinity is still going to be 1,000, right? On the other hand, it seems to be the case that if we could make our sum smaller enough, then it would transition from diverging to converging. And it's not clear if that is a sufficient change to make that happen right there. So I would say that sums like 1 over n to the 1.2, those are exactly the ones that are sort of sitting in mystery land to me. It's very close to something that diverges, but I know it's smaller than a divergent thing. So maybe it still diverges, but maybe it got smaller enough that it converges. So let's see how we can sort of explore this. I made a nice looking Desmos graph here that you guys should definitely use to help you kind of visualize this thing. This is sort of a graph that is manipulatable relative to the pictures that you should see in the diagrams in your textbook this week. It's going to be really helpful for us. So what I want to do right now is we're going to pop over to this Desmos link, and our goal is to determine what integral can we compute that will help us determine if this series converges or diverges. So let's pop over to Desmos and see this link. I've already clicked on it and opened it, so here's what we're going to see. Oh, wait. I gotta go. I added a thing to it. Okay, now it looks like what we're gonna see when you guys click on it over there. So here is this Desmos graph that I made. And what I am seeing for myself here is this. 1. I have computed this function 1 over x to the 1.2. That is our function of interest inside of our sum, and it is the function that I am using to compute the heights of each of these blocks that are out here. Notice that each of these rectangles has a width of 1. Therefore, the height of the rectangle is equal to the area of the rectangle, right? Height times width is area, but if width is 1, then it's just height is equal to the area right here. So notice that what I've really done is I've said the series, right, the summation of 1 over n to the 1.2, the first term, a sub 1, will literally be exactly this area right here, because what I've computed is what is 1 over 1 to the 1.2. 1 to the 1.2 gave me 1, and therefore that's the total amount of area here. 2 to the 1.2 will be exactly whatever this height is right there, 0.435 or whatever we're getting for that guy right there, right? So what I've done here is these blocks, which hopefully to you look sort of like a Riemann sum, are really representing areas that are equal to each individual term in our sequence. There's a sub 1, there's a sub 2, Can't put subscripts on these text labels, which kind of bothers me. I feel like Desmos is like this close to being like the best graphing tool in the universe, and instead there's just little things. How can I not use subscripts and labels on a math graph? So anyway, here's a sub 1 in our sequence. Here's a sub 2 in our sequence, a sub 3 in our sequence. I'm representing them all as having area equal to their value in the sequence, and its area is also equal to the height because they all have a width of 1 right here, right? And so what I'm seeing right now in this scenario is this. The equivalent curve, f of x equals 1 over x to the 1.2, currently it's following, as we can see, the upper left corners of these rectangles right now. So what I can kind of see is this, is what's happening here. If I added up all of the area of the infinite number of rectangles that go out here, and by the way, I only made 5 rectangles, it just sort of stops right there, but that's okay. This is for visualization purposes right here. If I were to add up the infinite number of rectangles, that would truly be the actual value of the sum. What I am seeing here is that this curve always is below the total values of the integrals. So if I were to, for example, compute the integral of 1 over x to the 1.2 from 1 off to infinity, one of two things might happen. If that integral diverged, if I get the integral from 1 to infinity of 1 over x to the 1.2 diverges, what I can see from this graph is that our sum is larger than the value of the integral. And so if the integral diverges off to infinity, then it's certainly the case that the sum should also diverge off to infinity. On the other hand, we can visualize this very similarly. I put in a slider bar over here for A, and all A is going to do for us is shift everything over by 1 block right here. You should still notice that all these blocks still have this exact same area. None of the sizes of the blocks didn't change. Now the blocks are just touching all in the right-hand corners over here. And so here's the next claim that I could make. If it's the case that we integrated f of x from 1 to infinity and it converged to a value that we know, what I can see here now is that the terms of the sum live completely below that integral's value. All of these areas are less than the area that we would have computed if we computed the integral from 1 to infinity. And therefore, if our integral converged to a number, since our sum is less than the value of that integral, it will also converge. And that's really, really nice for us here. So just by clicking this back and forth, we can see if the integral from 1 to infinity diverges in this diagram, then it must be the case that because the sum is greater than the integral, all the sum chunks are a little bit above the curve, then so must the sum diverge because the integral diverged. On the other hand, if we picture our rectangles being shifted over 1 block, we can now see if the integral from 1 to infinity converges, all of the terms of our sum are below it, and so it should also converge. Now, notice I keep on referencing an integral from 1 to infinity, and it's certainly true that we have like an extra block of area that's not participating in the 1 to infinity stuff, but here's the deal. If our sum from 2 to infinity converges to a number, there's no way that adding one additional finite term can push it over the boundary. The only way that we can end up adding up a group of numbers and getting infinity, if the numbers are truly numbers and not an idea like infinity, then the only way that can happen is if we have an infinite number of numbers. There's no way that one of them will make a contribution. That's any distinction right here. So there's only one real small technicality associated with these two graphs that I'm showing here, and that's that technically in this sense, our integral from 1 to infinity converging would suggest that the sum from 2 to infinity converges. But it's definitely the case that if any sum from 2 to infinity converges, it must be the case that adding in one additional term will not affect its convergence or divergence. So what this graph of rectangles being our sum and curve being the comparative integral is showing us is, I'm going to say it one more time, all together here. If the integral from 1 to infinity diverges off to infinity, then since our sum is always above it in this graph right here, our sum must also diverge to infinity. So computing the integral can tell us what happens to the sum. Alternatively, if we compute a sum of an integral from 1 to infinity and it converges, then so must our sum also converge because our sum will live completely below the curve that's out here. And this is great simple news for you guys. This just says whatever the expression is within a sum, 1 over n to the 1.2, we can just compute the equivalent integral from 1 to infinity of the equivalent function inside of an integrand, If the integral converges, the sum converges. If the integral diverges, the sum diverges. That's a pretty nice clean takeaway from this graph right here. So again, I would encourage you to click back and forth on A and convince yourself of these two things right here. The other good news is that this is only one of the two topics for today as the integral test. The other one is estimating sums. We're going to use exactly this graph with A equals 0 to help us out in a little bit. So I'm going to leave it right here, and we will end up adding in one additional expression right here to help us out with some estimates later, but that doesn't matter for us right now. So what I want to do is come back to Microsoft Word and let's kind of state this conclusion right here. So what we just determined is that if we want to know if this converges or not, then what we can do is compute the integral from 1 to infinity. If the integral converges, then the sum lived completely below the integral, and so the sum should also converge. On the other hand, if this integral diverges, we could, or sorry, if the integral that we're going to express from 1 to infinity diverges, then we can equivalently conclude that this sum must also diverge. So let's go ahead and compute this integral and see if this sum is going to converge or diverge. So here I can do my sum from 1 to infinity of 1 over x to the 1.2 dx. I'm going to rewrite this like a power rule, like I know I want to see this, x to the negative 1.2 dx. When I go to perform integration, I'm going to add 1 to the power, so I know I'm going to get x to the negative 0.2. I know that this is like 1/5. If I were to take the derivative, it would bring down a 1/5. I don't want 1/5, I want 1, so I'm going to need 5 copies of it. So I think a negative 5 right there is our appropriate coefficient there. Take a moment and take your derivative of this and convince yourself that it's this. Okay. This I am evaluating from 1 to, and I'm going to try and be appropriate right here. I'm going to put that in quotes to really say this should be equal to the limit as, what do we usually say, like t goes to infinity of negative 5x to the negative 0.2 is evaluated from x equals 1 to x equals t. Right? T is what's tending off towards infinity there. This is just me more formally writing. This is the limit statement like I should if I'm being responsible. And so negative 5 is the coefficient on the outside. I'm getting 1 over t to the 0.2 minus 1 over 1 to the 0.2, right? That's x to the negative 0.2 right there. What I can see, oops, I forgot my limit statement right here. Limit as t goes to infinity of this stuff right here. It looks like as t goes to infinity, this term is going to go to 0. It looks like this term is just going to be 1. And so it looks to me like that integral has a total area underneath it of 5 as we go from 1 to infinity. So coming back to our viewpoints over here, what I am seeing is the area from 1 to infinity is going to be 5. Our sum lives completely underneath that. So its value has to be less than 5. Now, granted, we're off by 1 term. There's no chance that this 1 term is going to have enough area to bump 5 up to infinity. And so I'm still comfortable concluding that because the integral from 1 to infinity converged, the sum from 2 to infinity converges. And if the sum from 2 to infinity converges, the sum from 1 to infinity must also converge because one additional point will never be the distinction between convergence and divergence. So that worked out kind of nice right here. Pretty nice and easy, right? And so I think I can say, since the integral converged, seems that sum must also converge because I can see the area that is equal to that sum is completely below the area that is equal to 5 from the integral right there. And by the way, just before we go conclude this, I really just got to say, like, just remember that you absolutely cannot picture this. What I know from last class is that if I just delete this 0.2, like how much did our graph really just change? And again, watch this. I'm going to now include the 0.2. Look at how tiny of a difference we're seeing. And what we know is that this graph diverges. That graph converges. I am telling you, it is not humanly possible to judge the convergence or divergence by looking at a graph. There's just no way. these two graphs, I can't tell the difference between the two unless I literally watch the change happen. One of those goes off to infinity. One of those has an area of 5. This is the difference between the number 5. Here's the number infinity on your screen right now. Here's the number 5 on your screen right now. It is such a subtle difference for such a massive difference in the total area that we're seeing under the curve or associated with the sum. So this is just to say, do not ever think that you can look at a graph and judge if an area converges or diverges. It is not obvious under any circumstances to anybody, just visually right there. So it's necessary that we compute that integral to see what's going on. So this is what we're going to call the integral test. The integral test says we would like to judge if a series, an infinite series from 1 to infinity, converges or diverges. If we can say that our expression within the series can be rewritten as a function, again, we're kind of limited by that requirement right there, where this function is continuous, positive, and eventually decreasing, we'll talk about that in a minute, on the interval from 1 to infinity, then we'll be given that this series converges if and only if the integral, the associated integral from 1 to infinity also converges. So a bunch of things I want to unpack real quick here. We're going to do them. We're going to start by discussing if and only if. This says that the only way this converges is if the integral converges. So when we say if and only if, that also means then that the sort of opposite statement is also true. If this integral does not converge, then it's not possible for the sum to have converged. This is if and only if. The only way for this sum to converge is if the integral converges. Therefore, if the integral diverges, the sum must also diverge. So this is sort of our way of writing those two side-by-side statements as one statement with an if and only if right there. If the integral converges, then the series converges. If the integral diverges, then the series diverges. And so we can write this as one statement with that if and only if right there. All right. So some other notes about the integral test here. All right, let's look at some other things that are associated with this. One, what's up with eventually decreasing? Well, one thing that we know here, and I'm going to kind of pop back to our picture over here for a second, is that we should probably remember things like the only reason that this sum right here, that this sort of Riemann looking sum is underneath this curve is because this is a decreasing curve, right? This is our right-hand Riemann sums, our underestimates of our integral if the function is decreasing, and now I come over and I say, and our left-hand sums are overestimates of the function if we are computing a Riemann sum there of a decreasing function. So kind of notice that these are only really properties of a decreasing function, but kind of check this out. If our sums terms were increasing in size over time and we're accumulating an infinite number of them, we're sort of obviously diverging. The only integrals that are even candidates for convergence are ones where the numbers that we're adding are sums. The only sums that are candidates for convergence are ones where each additional term is smaller than the previous, because those are the only ones where we're eventually like not accumulating anything else and we're converging on a value, right? So it's just got to be the case that we're decreasing. But all this is saying is that technically we don't have to be strictly decreasing forever. It might be that our curve like increases for a minute. Sorry, I'll do my hand graph here visually. So it increases for a minute, but then if it decreases for the rest of all time after that, we're good with that. As long as there is some point on our graph where at that point from then on we're always decreasing, that's the definition of eventually decreasing. We eventually hit some x value location where the function is decreasing for the rest of all x's forever off to infinity after that. And we can say that using our fancy math notation here. We mean that there must be some x value that I'm going to call n, such that for all x values beyond n, f of x is a decreasing function. Or I could have even said f prime of x is less than 0 or something like that. Another thing that's going on here. We can also use this integral test to judge the convergence divergence of sums that don't start at 1. Notice that sort of we said in our statement right here, it had to start at n equals 1. It's technically true that these sums can start at any lower bound value down there. All we really need is for the lower bound of our integral to match the lower bound of our sum, and this will be good right there. So there's really sort of a general a that we can think of for our lower bound. It's just incredibly common for that number to be 1. Next, we might need to determine if a function is decreasing, right? Decreasing is a requirement to use the integral test. So you can't go ahead and start computing integrals to help you determine convergence, divergence if we don't know that we're decreasing. Some functions, it's not obvious if they're decreasing, and so you need to remember that you know Calc 1. In Calc 1, we definitely spent time on these types of things where we said, listen, if you want to judge if a function's decreasing, then you can take the derivative of that function and decide if it's negative over the interval of interest. We're always interested in the interval of interest being like 1 to infinity or whatever our lower bound is off to infinity. So it might be the case that to use the integral test, you may, in some situations, need to take the derivative of a function and show that it's negative from 1 to infinity so that you've proven that you've satisfied the requirements of the integral test. The final note that I have about the integral test is that just because the convergence of the integral will match the convergence of the sum does not mean that the value of the integral equals the value of the sum. And I hope that that's relatively obvious by looking at the picture again. The actual area that we're getting in the rectangles is clearly not equal to the rectangle or the area that we're actually getting underneath the sum. But I would like to point out, it does seem like with later and later and later terms, it seems like this error that we're seeing out here. Sorry, I've been moving my mouse in the wrong place. It looks like, right, again, the area under the curve is clearly not equal to the area of the rectangles necessarily. But it also does seem like the amount of error, like the white gaps in between right here, it seems like our error is getting smaller and smaller because so many of these decreasing functions are going to have slopes that approach a slope of 1 as n goes off to infinity. And if that's the case, then we should expect the errors to be smaller and smaller and smaller as we go out there. But that's we'll bring that up here in a minute. Right? So again, just because this integral was equal to 5, under no circumstances am I trying to say that the sum's value is 5. I know that the sum will converge. That's all I've concluded by saying that the integral's value is 5. So what conclusions can we draw from this? Oh my gosh, I'm doing the dumb thing again. Sorry, I'm going to repeat what I said with the correct screen on again right here. Just because we saw this integral converge to 5 certainly does not mean that the sum's value is 5. All we can conclude is that because the integral converged, the sum will converge. That's all I know. It's going to converge. Attempting to make estimates of what it will converge to should not be done by just looking at the comparable integral associated with the sum. So what's the conclusion that we want to take away from this? And I'm just going to jump right to it. What's the most important conclusion that we can take away from the integral test? Well, when does the integral test even really help us? What the integral test is helping us do is it's saying in any sums where you can't determine if it converges or diverges, but you could compute the integral of the representative of the sum, a sub n, those are the places where the integral test is going to help us do something we couldn't have done before, right? So most interestingly to us is that we saw in the previous examples that previous class that we were looking at our geometric sequences. Well, there's a related group of our sort of our rational sequences, things of the form 1 over n to the p, that we haven't really discussed, haven't really pinned down any values for. What I am interested in is kind of knowing about the convergence of all these things. What does the sum of 1 over n to the 0.2 look like? What does the sum of 1 over n to the 7th look like? What does the sum of 1 over n to the 1 look like? That one we already know the answer to. That's our harmonic. But there's a whole family of these out here, right? Any power that we're seeing out here is a rational function. I want to know which powers on n, given 1 over n to the p, are going to cause this to be a convergent sum. Which of the ones are going to cause this to be a divergent sum? Remember in our last video, we checked in on this convergence of a geometric series. I think this is our last example in the previous video. We asked, does this converge or diverge? What values of x cause this to converge? If so, what does it converge to? What we ended up determining was that this one parameter family of series, right? It's a one parameter family because you get to pick x. X can be anything, right? We determined this one parameter family of series converges whenever x was between -3 and +3, not including -3 and +3. And then we found what it converged to is like x over x minus 3 or something like that. We referred to that interval from -3 to +3 as the interval of convergence. It's an interval of x values that would cause the one parameter family of series parameterized by x to converge. Very wordy right there. I think the idea is simpler than the sentence I just said. So very, very similarly, we're asking a very related question. Just like here we said for what values of x or what interval of x values cause this series to converge, here we're saying what values or intervals of values for p cause this series to converge or diverge. So the good news for us is that things of this form are always going to be continuous. They're always going to be decreasing, and they're always going to be positive as long as we are starting with positive values for x right here over that bound from 1 to infinity. So this says we should be able to use the integral test to make judgments associated with this. Right? The other good news is that we've actually already done several of these. We have already shown that if p is equal to 1 in this case, that gives us the harmonic series. And we already have seen, we've proven it twice, the harmonic series diverges. You should just tattoo that to your forehead if you can't remember if the harmonic series converges or diverges. It's that important for the rest of the semester. We also just did the example where p is equal to 1.2. That was the first example we just did. We saw that the integral gave 5, and therefore the series that it's associated with should go ahead and converge. So I am already sure that p being 1.2 caused convergence. I'm sure that p equals 1 caused divergence, right? So what we're trying to judge here is out of all the p-values that we could pick, which of the ones cause convergence? Which of the ones cause divergence? So let's go ahead and check out some other values out here. And let's go ahead and check out something like on the other side of p equals 1. So let's go ahead and do like p equals, I don't know, 0.8 right here. Then in this case, we're wondering, does the sum of 1 over n to the 0.8 converge or diverge? Now, I'm going to kind of tell you how I know the answer to this question already. And the answer is, hold on, let me double check real quick, make sure I'm not lying to you. Yes. Our very next section in the book, section 11.4, is the comparison tests. All right? That's going to allow us to compare between two different series. And if one converges, the other converges. If one diverges, the other diverges, as long as we make the appropriate comparison. What I know is that all of the terms associated with this, all of the n to the 0.8s are smaller than n, as we saw in the harmonic series. We're dividing by a smaller number, therefore we should be getting larger overall terms in our sums. If the harmonic series of p equals 1 diverged, all of our terms in this sum are going to be even bigger. And so since this sum is larger than a divergent sum, this sum is also going to have to diverge, but let's hit this thing with the integral test to make sure that we are doing the right thing here, right? So I should be doing the integral then from 1 to infinity of 1 over x to the 0.8 dx, which is going to be, I'll rewrite this as 1 to infinity of x to the negative 0.8 dx. This should be giving me, I add 1 to the power, and I'm going to get x to the 0.2. That should cause there to be a 5 down front, right? The derivative would bring down the 0.2. 0.2 times 5 is just 1, like the coefficient we originally had right here. And we're evaluating this from x equals 1 to, and I'll again just put this in our quotes right here. Technically, we should be using those limits right there. So I'll write this as the limit as t goes to infinity of 5 times, and we've got our t value right here, t to the 0.2 minus 1 to the 0.2. And what I'm noticing here is that as t goes to infinity, this is now like 5 times infinity minus 1. And that is going to diverge off to infinity. Therefore, the sum of 1 over n to the 0.8 diverges. And it diverges because the associated integral from 1 to infinity diverges there. And that's good. That showed what I thought we were going to see. Since 1 over n.8 is greater than 1 over n, all of the terms in this series are larger than all of the terms in the harmonic series. The harmonic series went off to infinity, then adding up even bigger terms should also cause us to go off to infinity. That's more of a comparison test related idea and coming up in next section, 11.4, but I don't think that's beyond your reasoning skills to understand that, because honestly, we've sort of sneakily been doing comparison tests this whole time, and honestly, This is a comparison test. We're just not comparing a sum to a sum. We're comparing a sum to an integral. So this is not referred to as a comparison test because it's not a comparison between two series. But we just estimated areas, right? The area associated with this integral has a direct relation with the area that we can interpret with this series if we picture this series as being rectangles of width 1 and height equal to the value of the series. Then the area of each rectangle is the height of the rectangle, the value of the term of the series, and adding up those areas is equal to getting the sum of the series there, right? So this is a comparison test. We're just comparing integrals to series, so it's not called a comparison test. So in general, sums of this form are referred to as p-series. Even the book states it. They agree with me that this is probably the single most important family of series for us to know because we're going to compare against these constantly. Because geometric series we can already handle. Series where we can't come up with a function to describe what's going on the inside in a sub n, those are just really freaking hard for 1,000 other reasons. This is going to give us a lot of comparative power. There's going to be a ton of situations where we're going to be able to compare integrals to p-series where we're going to be able to compare series to p-series. We know now everything about p-series. We're going to make our claim in a second, and that's going to allow us to make a huge number of comparisons that allow us to know about tons of series convergence or divergence that we could never directly investigate by just determining if they are larger or smaller than a known p-series. So kind of the thing that I'm seeing here is that it seems like if the p values are bigger than 1, it seems like we're going to experience convergence. And it seems like if they are 1 or less, it seems like we're experiencing divergence here. And so based on these observations, this is basically what we're saying. P series, 1 over the series of 1 over n to the p, will converge if p is bigger than 1, meaning we are we're making the values slightly smaller than the harmonic series, and it will diverge if p is less than or equal to 1. So maybe you can now kind of actually see what makes the harmonic series so special. The harmonic series is sort of the smallest thing that still diverges to infinity, right? Any p value that's smaller than 1, that's larger than 1 will cause us to converge, right? So the the harmonic series again it's the sort of in a sense it's one of the smallest infinities we can build. When things get just slightly smaller than that, they end up converging, and we'll see that because if p is like 0.99, then we converge. But if p is 1.01, then we continue to diverge down there, right? I said that backwards. Oh my gosh. If p is 0.99, then we diverge. If p is 1.01, then we converge right there. P equals 1 is our kind of our cutoff between convergence and divergence, and p equals 1 is divergence, right? So again, p equals 1, our series diverges. P equals 0.999999, and we're going to converge, right? Which is really kind of an interesting thing that there's sort of got to be this threshold between infinity type stuff and not infinity type stuff. And the harmonic series then therefore represents that it's the smallest quantities we could build in a series and still have the series diverge. So what I say when I say check this out in Desmos is I want to show you guys, by the way, that integrals like this can be handled by Desmos. So let's pop back over there, and I want to confirm, sorry, I keep on highlighting the wrong screen here. I want to confirm this statement in Desmos, and I'm going to do it not graphically. So check this out. I'm assuming most of us don't know that Desmos can do this. So let's pop over to our browser here. I'm just going to go, okay, give me a couple down here. All you should be doing is just looking at what I'm typing in down here. I guess I got to zoom in my screen so you can actually see this. I don't care about the graph at all. I just care about what I'm typing in right here. In Desmos, I can do the integral. I can do the integral from 1 to infinity, and I'm just typing infty is infinity. What are we computing the integral of? 1 over x to the p dx. It asks me if I'd like to add a slider bar for p, and I say yes. We can see that when the p is 1, this is the harmonic series integral that we're looking at, and the integral diverges. It's undefined. If we make this number larger than 1, we are converging to a number, and we see convergence for any value of p that's larger than 1. And as soon as we go beneath 1, we see that we're undefined. and that we will get divergence for all remaining values that are out there, right? So just watching that undefined switch to being a defined number after 1 is our Desmos, this is our modern version. Again, this isn't proof, but this is great evidence that what we just saw, it seems to be true out there, that if you have a P series with a P that's greater than 1, greater than, not greater than or equal to, P equals 1 is the harmonic series which diverges. Any value of P bigger than that, we're going to converge to a value, right? So that's sort of our Desmos integral calculator version of these. And by the way, like, what nice stuff right there. Anytime you have a one parameter family of anything, you should be throwing it into Desmos and getting a slider bar to help you investigate it. So this is good. So that we just literally discovered the convergence or divergence of an infinite number of series. Anything that can be written as 1 over n to the p, we can talk about its convergence and divergence as a just based on that p series rule right there, and it's really simple. Meaning, I don't even know that I have any examples to do here. The series 1 over n to the 14th is going to converge because 14 is bigger than 1. The series 1 over n to the 1/14th is going to diverge because 1/14th is less than 1. Not a lot of super enlightening things to say about this, but again, this just told us about the convergence, divergence of an infinite number of series that are going to be things that we're going to be able to directly compare to series we don't know in future sections. So this is crazy useful. It's not useful as like a standalone fact. It's useful because we've just created an infinite number of items that we can now compare against for the future series that are going to be more difficult to handle. So we're very much setting ourselves up for a future comparison by identifying this P series idea right here. We know about everything of the form 1 over n to the p now, so we can always make comparisons against those things. So that's sort of our part 1. Part 2 of this section says, well, if we can determine convergence or divergence, the next thing we want to do, if we know it converges, is ask, well, what do we think it converges to? So suppose we'd like to know the value of this series, the series 1 over n cubed. Since it's a p series, with p being greater than 1, we know it converges. I don't need to do any math. If it is of the form 1 over n to the p, and p is bigger than 1, converges by p series, done. That's all you got to tell me to convince me. I don't need to see an integral test for this guy right here. You can say p series with p greater than 1 implies convergence. Done. That's all we need for that guy. So how would we estimate this thing? Well, I'm going to suggest that there's a pretty simple, naive estimate that we could do. And what I would say here is that S sub n is approximately equal to the true sum itself. Right? All I'm really saying here is, well, I don't know, just take the first couple terms. That's a pretty good estimate right there, right? So I might come up with something like S sub 5 equals 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed. It turns out that this is going to end up being probably really close. Why is this going to end up being really close even though I only grabbed 5 terms? We'll kind of again realize over here, it seems like the bulk of what's being accumulated here is in these large ones out here, right? All these further rectangles that are further out there, because this is always going to be a decreasing function that we're looking at, are always going to contribute less and less and less. So we're getting this diminishing returns idea. The more terms that we include here, each one of them is going to make a smaller contribution than the one before. So I kind of think that I've captured a bulk of the value of this series by just looking at the first handful of terms. This is obviously our like lazy person's way of doing this right here. Maybe we want to say, listen, we shouldn't just look from 1 to 5. I still want to make this consideration from 1 to infinity, but I don't want to have to do an infinite number of sums right here. So how can we do this a little bit smarter? Right? So what we saw was that the integral test will help us judge if a sum will converge or diverge. We also know that if a series converges, it doesn't necessarily mean that we can compute the value of a sum, right? Just because we found the integral converge to 5 up above didn't mean that the series value is 5. But we can use this same graphical idea to help us visualize how we might place upper and lower bounds on the value of the series, not the integral. The integral will be the bounds for the series. So what we're going to do is we're going to come back to the same calculator, and I'm going to add one line. I actually think I can literally just copy and paste it in there. I'm going to add one extra graph for this guy here. And let's come over here and do this. I'm going to get rid of this guy. Let's come back to our browser over here. I'm going to get rid of this guy. I'm going to go back to not having this be obnoxiously large. And I'm going to throw in this addition. Oh, I even left a spot for myself up here. I'm going to graph a new function, g of x, and importantly, I'm going to place my a value over here. Okay. I'm kind of hoping that I don't really need to say too much about this for you guys to see what our idea is right here. Right? It looks to me like in this case, both the black curve and the red curve are both some goodness of estimate for the actual value of the sum. Hopefully you can see quite obviously that the area underneath the black curve from 1 to infinity is less than the value of the sum, and that the area under the red curve from 1 to infinity is more than the value of the sum. It seems like these two very related graphs that are just a horizontal shift of one another are perfectly good upper bound, lower bound estimates for the actual value of the integral, or of the sum of the series there, right? These two integrals can help us make this estimate right here. The only thing we are going to need to account for is we want two versions of the same function, but one of them needs to sort of start one space later, right? The x values have been shifted by one relative to each other, right? So here's kind of combining these two thoughts now. I know that if I want to come up with a good estimate for this function, I should just straight up add the terms. If I want to know what a sum is equal to, you add up all the terms. With an infinite number of terms, we can't do that. But maybe sort of the responsible thing to do is to not estimate the first ones that are the big parts of it out here, right? Maybe we just add those up directly. So maybe we do something like say, truly get the first 5 terms of our sequence or series, and then we'll know that all the remaining parts that we want to accumulate are going to be more than the area underneath the black curve out there past where we've accumulated, and they will be less than the area underneath the red curve beyond where we've already accumulated out there. All right? I think that this is such a nice graphical idea. I feel like I could literally have just shown you guys this graph with no words on paper or out of my mouth, and you still kind of would have like inferred this idea here, right? Um, pretty natural idea of ways to put bounds on the value of that sum because we really want to know the area of the boxes, not truly the area underneath the curve, right? How full circle we've come now. We use boxes to find curves. We're using curves to find boxes. This is great. So let's come back over here and kind of do this here, kind of make this statement here. So how can we use integrals to estimate values of series? Two-step process. Step one, compute the partial sum, S sub n, of the first n terms. I verbalized it. I threw it in my graph as the first 5 of them. I did that up here, right? We added up the first 5 terms. But we know that's not it. We know that there's still an infinite tail that follows beyond that. Then we're going to estimate the remaining value as being bounded by an upper bound and a lower bound integral, right? We've got an upper bound integral that's guaranteed above. We've got a lower bound integral that's guaranteed below. So this is saying, let's do a little bit of the exhausting work of truly doing the sum for the first couple terms. Once we get tired of doing that, we'll estimate the remaining area in the tail, the infinite tail, with integrals, because that's more of a one-step deal to capture the remaining infinite tail that's out there. So we can write this as one big equality. This inequality kind of looks gross right here, but this is really not that bad at all. Our goal is to estimate the true value of the series. That's what's sitting right here in the middle. Our lower bound for this is going to say take the actual exact value of the series out to the nth term. Then our lower bound will be starting at the n plus 1th term, integrate the rest of the way out there. Our upper bound will instead say, compute exactly the first n terms, and then picking right up at the nth term, compute the integral from n on out there. I'm kind of hoping that you're sitting there being like, wait, what just happened? Why do we have n and n plus 1 right there? Those don't seem to make sense as the bounds right there. Here's the thing that's happening. Notice that when we went into Desmos and we did g of x equals f of x minus 1, that was a shift to the right. You should notice that this translates for us into a new lower bound of f. Here is that f of x minus 1 thing that we're doing, and notice if we just start this, because this was shifted 1 to the right, our lower bound needs to start 1 to the right to be equivalent. You should convince yourself for a moment, if you're not convinced right now, that these two integrals are exactly the same value. This says move your graph 1 to the right, and then start counting from 1 to the right relative to this graph right here, we're going to get the exact same areas that are out there. So when we did this f of x minus 1, that was really a integral shift to the right by 1, and that's why we have increased a lower bound to the right by 1. Let me make one more argument to you how you should like remember this right here. Also remember that since f of x is required to be a decreasing function right here, if we start our integral later, then we should be getting a smaller number, and it's definitely the case that we're looking for our lower bound to be on the left. If we start our integral earlier, we should expect to get a larger number, and that's why this is our upper bound stuff on the right. So starting your integral later with a decreasing function should get you a smaller value. It's associated with a lower bound out here. Okay, last thing about this inequality, and then we'll go use it. The other thing we can do is we can define the remainder, the part that we are off by relative to our partial sum, to be the difference between the partial sum and the true series, right? So this is not like a remainder, like the little like triangular gaps, like the remainder, like our error between our integral and our Riemann sum. This is saying if you've only added up the first 7 terms, then you've missed the 8th term off to infinity. So the 8th term off to infinity would be the remainder in this case, right? So all I'm going to do is I'm going to take this inequality up top right here, and I'm going to subtract s sub n, the partial sum of the first n terms, off from this guy right here. In the middle, that's literally the definition of how we're defining remainder. It's the remaining terms that are beyond the nth term out there. And over here, we're just straight up getting these integrals. So these integrals are now basically saying to us, we can calculate how much stuff is left in our sum by just computing these two integrals. This will give us a lower bound and an upper bound on the length of on the area accumulated in the tail of any series that's out there. It's got to be between those two integrals. Notice that the use of these inequalities still requires that same restriction that our function is continuous, positive, and decreasing on this closed interval from n to infinity in there. Right? So let's look at an example of this guy, and we'll go ahead and call it a day here. Let's estimate the value of the sum of 1 over n squared, and let's do this by first computing the first 5 terms exactly, then using integrals to estimate the remaining area that we're going to see. All right? So, step 1, get s sub n. In our case, we're going to look at s sub 5. We want the first 5 terms. This is going to be 1 over 1 plus 1 over 2 squared is 4, 1 over 3 squared is 9, 1 over 4 squared is 16, 1 over 5 squared is 25. So this is a pretty good estimate, but it's only it's exactly correct for the first 5 terms. I want to know what this is actually going to be. I'm going to get this as a decimal right here. So 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25. And I'm getting 1.4636, and then all ones forever. 1.4636, 111, and ones forever out there. So that's a reasonable estimate right there, but I want to place good bounds on this guy right there. Now, let's get integral estimates for the tail. The tail beyond n equals 5. Right? So what that says to me is I want to know what is the integral from 5 to infinity of 1 over n squared, or 1 over x squared dx, and the integral of 6 to infinity of 1 over x squared dx. So I'm just going to call these collectively the integral from b to infinity of 1 over x squared dx, so I just don't have to do the work twice here. So the integral from b to infinity of 1 over x squared dx, we're going to write this as the integral of x to the negative 2 from b to infinity, which dx, which is equal to negative x to the negative 1, limit as t goes to infinity of b to t. Right? So I'm seeing here negative 1, let me get my limit in there. It matters now. Okay, okay. Limit as t goes to infinity of the negative of 1 over t minus 1 over b. I'm seeing that as the limit as t goes to infinity of 1 over t is going to be 0. The negative is going to multiply by the negative inside to get a positive, and that's just going to give me 1 over b, where uh, where b equals 5 and where b equals 6. So that's going to tell me we just got out 1/5 and 1/6 right there as the two bounds on the remaining tail of the sequence. That says to me the sequence, and so let me just say it like this. Here we go. So integrals tell us no, we got 1 through 5. So this will be the integral from 1 to 6 to infinity of 1 over n squared is stuck between 1/5 and 1/6. What I now want to say is that s sub n plus 1, oh sorry, I'm going to rate this as it should be. S sub 5 plus 1/6 is less than, sorry, and I keep on writing these. So another thing I know is that these are not equality right there, because if they were, the only way they'd be equality is if our curve was literally flat. Otherwise, every single bit of our integral is going to be off by a little bit from our rectangles out there. So there's no way that we're getting equality here. Right? And notice what's going on in the middle right here. This says first add up the first 5 terms of your sequence, then add up the 6th to infinitieth terms of your sequence. That's just the whole dang sequence there, right? So here what I'm really getting then is I'm getting my s sub 5 plus 1/6 is less than the sum from n equals 1 to infinity of 1 over n squared. The whole thing we wanted to actually estimate is less than s sub 5 plus 1/5. And so now I just got to go to my calculator and do these two calculations, and we'll see what we're going to get. We started with this 1.463611111, right? I'm going to go ahead and add to that 1/6, and that's given me 1.630278 is less than our desired sum. And now I'm going to go ahead and subtract 1/6 and re-add 1/5. I'm just doing the addition and subtraction of my calculator to keep all my decimals out here, and I am getting 1.66361111 forever out there. So now we've come up with we know that our estimate here is better than it could have been by just using integrals, because we got the exact answer for the first 5 terms, which is where the bulk of our values were located. So we didn't have error in the big error places. We then used integrals to estimate the remaining tail from the 5th location on. And by the way, very difficultly, it can be shown that this is equal to pi squared over 6th. Go ahead and say, what the hell, for a second right now? How is that? Where did pi just come from? That should be you should be almost angry about that. I know that this proof is not easy to show that this is actually the actual value of that sum, but I do know that probably, well, top 10 smartest humans that's ever lived, Leonard Euler, did figure it out. He's one of the 2 people that the joke is that nothing's named after him, because if we named things that he discovered after him, then literally everything would be named after him. So instead, everything gets named after the second person that discovered it, because otherwise everything would be Euler's this and Euler's that. So yeah, so he's the dude that figured out that this is actually equal to pi 6th, and you can go and check in your calculator. What do we get for pi 6? We actually get pi squared, or sorry, not pi 6, pi squared over 6. And we're getting 1.64493. So it does look like we did a pretty good job of estimating this. We got this down to being within about, what, 0.015 Pretty decent margin of error right there by doing a little bit of addition, a little bit of integration to make an estimate associated with these guys here, right? So again, our kind of idea here is we don't want to literally do a whole bunch of addition to estimate values of series. We should do a little bit of an addition at first since we can get some exact parts to our series. But for all the parts where there's going to be error, we'd like to have a lower bound and an upper bound estimate on that guy. And the way that we can do that, again, I want the thing that you take away from this chapter to be this diagram right here. We've got an upper bound, lower bound integral that can help us discuss this stuff. So kind of the one bad, oh, I'm dragging the wrong thing here. Kind of the one bad thing about this well, it's not a bad thing about this picture, but again, realize that what we just did is exactly what's in this picture. What's in this picture is we exactly got the area associated with this guy here. And then we said for all the parts remaining, we know that our true area will be something between the area under the red curve and the area underneath the black curve. And so these represent our bounds for what must be the remaining area in the infinite tail that's remaining out to the right out there. So this says we got the first 5 terms exactly. We got the 6 through infinity terms approximately. And adding that exact stuff together with the approximate stuff gave us a much better bound than we could have got if we just said, I think my point estimate is, the first 5 terms. Or if we said we think our integral boundary estimate should be just the integrals from 1 to infinity and 2 to infinity. Notice how much more error that would introduce if we use the integrals early. How much more error would that introduce? Look at all this honking area out here above A1. All of this error would be introduced into that inequality. So it matters that we compute a couple terms exactly. Then we go ahead and compute the remaining tail as our estimate using the upper and lower bound integral, so we're not accumulating huge amounts of error that are typically associated with our integral in our early terms have lots of error. Our integral in our later terms typically have much less error. So that's why it's usually good to compute the first couple terms exactly right there. So that wraps it up for us here today. And again, I kind of want you to notice like today is a great section for preparing us for the rest of this chapter out here. I don't think the hard part was our P-series stuff, but I think that definitely this is our biggest takeaway from today that we're going to reuse. And when I say reuse, I mean abuse. We're gonna use this stuff so much to make comparisons in the next couple sections out here. P-series is really, really solid information for us to know. And again, picturing this graph, highly, highly valuable for us imagining what's happening with these series. But also remember that the major limitation, oh my gosh, if I dragged the wrong thing one more time. Remember that our major concern about these graphs, not concern, but like the thing that we can't judge, remember, we're looking right now at a convergent integral. We're looking right now at a divergent integral. Remember that you cannot see the difference between convergent and divergent graphically, but you can see an appropriate way to make estimates or place boundaries on a value graphically, or to estimate convergence, divergence by those greater thans and less thans graphically here. So these graphs are very practical, but they definitely have their limitations. But I hope that you have this image kind of burned into your brain right now. Oh my gosh, if I move that thing one more time, freak out. For the rest of this chapter out here. That Desmos link will work for you. You should be able to click on, wait, where'd it go? Oh yeah, you should be able to click on this link and it'll take you to exactly this graph. The only things that aren't in the graph on the link are g of x equals f of x minus 1 and the integral stuff that we did down there at the bottom to verify our p-series thing that I actually already deleted right there. Those are smaller things right there. So, hey, would you look at that? I made a video in an hour. Good job, Tony. So as my final comment here, I'm going to tell you kind of our upcoming things. Remember that we have Thanksgiving break coming up next week. We have the entire week off. What I'm going to be doing is I am going to be distributing on Friday to all of you guys something that I guess is going to feel like a test, but in my mind it's not a test, and in your mind I don't want you to really treat it like a test. You should be thinking of it as all the homework assignments that I should have been assigning by hand if I had the time to be doing that up until right now. I'm going to put this out in Canvas by Thursday, or I shouldn't say Thursday when I really mean it's probably going to be by Friday. But the point is, I want you to have Thanksgiving break to do this, to do it nice and casually on your easy days that you can. This won't be due until midnight of Tuesday after Thanksgiving break. So if you are insistent that Monday through Friday of next week is going to be days off for you from school, then it should still be the case that Saturday, Sunday, Monday, Tuesday should be plenty of time for you to knock that guy out. So in a sense, this assignment that I'm going to post is doing the job of a test in that I'm going to grade your written work. But I don't know. I don't want you guys to be like, oh gosh, there's a test coming up. I'm picturing this as a way to sort of alleviate the large number of questions that I would otherwise want to put on the final exam. So by doing this sort of large test or large see, I just said it right there. This large homework assignment in lieu of a test is going to kind of help me be able to trim down the stuff that I'll put on the final exam that we'll see in what 3 or 4 weeks coming out here. So long homework assignment will be assigned at the end of the week here that will cover our previous chunk of sections, last couple 3 4 weeks of topics out there, and it will be due midnight on Tuesday after spring or after Thanksgiving break. When we get back after Thanksgiving on that Monday and Tuesday, I'm going to pick up with our regular videos. On section 11.4, we're going to get the comparison test, which is going to say to us, let's compare integrals that we cannot discuss with all the ones that we already know how to discuss the convergence and divergence of, namely our geometric and our p-series integrals. And in section 1.5, I think that's where we get our alternating series. That'll be talking about the ones that all have like a -1 to the n up there that do their bouncing back and forth. We'll talk about those series in section 11.5. Those are the ones that I think we're going to be hitting the week after Thanksgiving. Ooh, I do think we're actually hitting 3 chapters that week after. 1.6, absolute convergence, the ratio and root test. I do think we're hitting 3 sections here so we can get all this stuff in our last couple weeks, but that's okay. These are good sections. It's worth it. So that wraps it up for me today here. You should be expecting sort of a long form written assignment by the end of the week posted from me. And otherwise, happy Thanksgiving, and I will see you guys in 2 weeks.